Good afternoon, everybody. Welcome to today's webinar. My name's Alex McCutcheon. I'm a director of Unicom. We're very pleased to be hosting today's presentation, which is entitled Everything Changes in Motion Analytics for Data in Motion. It's very much a leading-edge topic, and this is in association with our conference, Real-Time Analytics, Making Better and Faster Business Decisions, which is on the 29th of January. Today's presenter, I'm delighted to announce, is Dr. Christoforos Anagnostopoulos. Christoforos is Chief Science Officer at Mentat Innovations, and he's a leading expert in this area, holding BA Mathematics from Cambridge and also a PhD from Imperial College. So without further ado, I'm going to hand over to Christoforos. Thank you.
Thank you very much for this. It's a pleasure to have the opportunity to give this talk for a very important topic. Just to give you a bit of background, I'm the Chief Data Scientist and co-founder of an exciting startup in London on software for real-time statistical analysis and machine learning. I'm also a lecturer in statistics at Imperial College London, where my research is focused in this same area. I'm going to turn on my webcam just to introduce myself to you. So thank you very much, everyone, for attending this. I will switch off the webcam later on during the presentation to make the look and feel a bit more compact. So the title of the talk is Everything Changes, and I'm going to focus on in-motion machine learning rather than analytics. The distinction is that analytics can involve very simple operations such as counting, and is mostly often focused on visualizing such simple aggregate statistics. In contrast, what I'm going to try to convey here today is the challenges of performing full-strength machine learning on top of real-time data streams. So let's take a step back and consider the use cases, consider the dream that big data has brought upon us. I'm going to mention a few examples. We've been working on all of these, but they are used here mostly to help you visualize the applications. Smart metering involves the introduction of IP-enabled connected meters in the whole of the UK, which will give half-hourly electricity readings automatically to the utilities and the national grid. At the moment, meter readings occur at best monthly and manually. Consequently, this is a huge step up in the instrumentation of the urban environment. The objective there is to offer postcode-level demand forecasting that will help balance the grid and therefore prevent shortages in energy and eventually lower energy prices. An alternative use case here is personalized tariffs and energy saving tips. By having a behavioral profile of each household and their consumption patterns on a daily, weekly, and monthly cycle, the utilities are able to offer advice on how they can optimize their usage and reduce costs. Another application is telcos. Telecommunications know the most about citizens today than any other organization or entity. The top 3 telcos know exactly where every single Londoner is at any given point in time. The objectives there can be several depending on who the client is. You might want to track and predict crowd movements by customer segments or demographic. And that's a huge third-party sharing opportunity for telcos. I'm going to mention straight from the beginning that there is a huge privacy risk here, of course, and this is exactly what we've been working with in collaboration with EY at Level 39 at Canary Wharf, where I'm currently located, in an attempt to offer privacy-respecting analytics and machine learning. But I'm not going to talk about that today. I'm just recognizing the risk. Computer network traffic involves the monitoring and analysis of packets that are being exchanged across computers, computer-to-computer chatter, in a large organization. This can be indicative of intrusions, as well as potentially faults. The objective there is to understand what normal behavior looks like and flag any atypical behavior as a potential threat. This is a complementary approach to the standard antivirus technology, which is signature-based in that it expects a certain type of pattern, a certain type of attack vector. Behavioral monitoring, in contrast, is slightly more agnostic. It doesn't make specific assumptions about the process. It learns what normal behavior looks like on the fly, and then eventually becomes able to detect atypical behavior on the back of that. What I should mention about computer network traffic is that it's truly a massive data source. If you take into account packets, packet sizes, communication data, metadata, as well as potentially system logs, we're talking about literally unstorable data. Even very powerful organizations are unable to store any more than a month of this type of data. So this is something that I will come back to, the inability to store the data set as a major constraint in what you can do when you're working in real-time data feeds. Business information services is another exciting use case here. Companies like Bloomberg and LexisNexis consume millions of documents per day. These include news posts as well as blog posts. And the objective is to extract meaningful information to reduce information overload for reputational tracking systems for big organizations, as well as journalistic investigative work. So this is another very interesting use case involving text analytics and natural language processing on a stream. So the list is truly endless, and I haven't even begun to discuss the natural area for these technologies, which is the Internet of Things and sensor networks. Indeed, sensor networks is where streaming data research originated from, and it still represents a major part of it, and I believe it will become, again, very important in the future as more and more physical environments are being instrumented, more and more physical objects are being IP-enabled. Consequently, we will have a huge number of very variable data feeds that yield information in real time about our environment. And the challenge there is how do we extract knowledge from these huge data pipes of data. So there are 4 components to machine intelligence in real time. And at this point, I'm going to switch off my webcam to give you a bit more space. Now, one component is the data. I've already discussed this a bit. Data streams are a continual source of information, like the ones that I mentioned before. Now, on the horizontal layer, you need to have 3 core capabilities in order to process these streams. One is statistical expertise. You need to understand machine learning and statistics in depth in order to be able to adapt these methods to the requirements and constraints of real-time data analysis. Most of this talk will be about that. But there are also 2 additional capabilities that you need to hold. Infrastructure is key. Infrastructure involves the ability to process these feeds without developing huge queues, without latency, and potentially in parallel, because the number of the feeds increases as well as their velocity. Finally, domain knowledge is also fairly critical in success of any learning and intelligent system. Domain knowledge might come in the form of a problem definition. That in itself is a huge challenge for any of you that have worked with real data and real business problems. Just identifying what the question that needs to be answered is probably one of the hardest parts. But also here, we need to find a totally different way of addressing the way in which domain knowledge continues to influence the learning system. Because in contrast to the classical batch paradigm, streaming real-time data systems are deployed and then are usually sort of left alone to do their job, and we need to find intelligent ways for the user to interact with the learning modules. So I'm going to discuss a bit all of these issues. And obviously all of this leads to real-time insights, which is the real objective. We're not doing this as an academic exercise. We're doing it in order to solve real-world problems. And therefore this needs us to consider very carefully how the output of our learning modules will actually be consumed. So that's another dimension of innovating in streaming machine learning and in-motion analytics. So let's go over these one by one and try to understand how in-motion data differs from big data. Let's start with statistical expertise. Now, the classical batch paradigm of doing data analysis, both in sort of small and big data, is that you store everything and analyze later. By analyze, we might mean something as simple as pulling a report or counting, to a very complicated task like a machine learning a problem such as machine vision, for instance. But in both cases, the paradigm is that you store all the data first and then you analyze later. And this process of analysis in most cases has an iterative nature. You start off with one type of report, you explore it, you look at it, it's not quite what you wanted, you pull another report. Similarly, machine learning tools will automatically iterate over the data set several times as they're trying to improve the objective function that you've ask them to improve on, a bit like reinforcement learning. So it's critical in almost all available statistical and analytic software that the data is in store somewhere so that it can be revisited time and again for the process to work. Now, this is challenged in the streaming data domain because you can no longer have the luxury of storing all the data. It might be that you can't afford to store it. For instance, in computer network traffic, it's literally impossible to store all the data generated by a large network in a large organization. It might be that you'd rather not store it because you want to avoid the cost, even if it is possible to do it. But in all cases, there's an issue of latency. If your system, if your learning system, your analytics engine relies on multiple runs over the data, as your data set grows, eventually your methods will slow down. Now, we might start a conversation at this point about how processors are becoming faster and faster and storage is becoming cheaper and cheaper, but the reality is that data arrival is also becoming faster. And it's no longer obvious that storage and processing power will outpace data arrival. In certain cases, it's certainly not the case at the moment. So there is a pertinent need for methods that do not require multiple visits over the data history, and that is the #1 constraint in the work that we do in in-motion machine learning. I've used the symbol of a shredder at the end to emphasize this fact, that the data passes through our intelligence layer, which is symbolized here by the Mentat logo, but we could have used another picture for it. And once it passes through the intelligence layer, it is then deleted as far as the machine learning is concerned. It has no longer access to the actual data points. It has to squeeze out all the information in the data on one glimpse, on a single pass, and extract any insights. So that is academically called online learning. You process each data point once, and you update your model rather than refit your model when new information arrives. That means that you store your model state somewhere, and whenever a new datum, a new piece of information arrives, you update that state rather than repeat the whole learning process from the beginning. I'm going to revisit that at great length as this talk continues. Now, a second requirement in streaming data analytics and in-motion analytics is the recognition of the fact that everything changes in real life. In all of the systems that I described to you, ranging from smart meters through to computer network traffic and instrumentation of large power plants, things change over time. Equipment ages, people change behavior, households change circumstances, a new baby comes in, or one child moves out. Consequently, we need to create fail-safes, safeguards for the possibility that the process might change. And learning needs to be continual, so that novel information is always taken into account into the learning paradigm. To give you a very simple example, if you're building a decision tree and you've used data for the last 6 months to build your decision tree in order to make a decision, say about the positioning of an online advertisement. The rules that you've extracted might be valid for 1 or 2 days or maybe even a week, but at some point they will become outdated because the user behavior has changed, your website might have changed in other ways. Consequently, in in-motion analytics for in-motion data, it is critical for all of your methods to have an inbuilt ability to handle change. What does change mean from a technical perspective? I'm not too sure how many of you here are of a technical background, and for this reason, this talk has 2 components, one technical and one less so. But for those of you that are interested in the technical side, it depends on what methodology you're using. If you're a statistician, and you're fitting a model with some parameters, the fact that the data generating process is changing implies that the parameters of your model are changing over time. If you're a data miner, then it is the patterns that you're looking for that will be changing. For instance, the rules in your decision tree. Similarly, if you're a machine learner, then the rules and the patterns that you're trying to extract are changing over time. So we're going to talk a lot more about this later. So to sum up, you have online processing, the need to have learning technology that doesn't require storage of the data, and adaptivity, the ability to track changing, evolving systems as the 2 main considerations in statistical methods for them to be suitable for streaming real-time insights. Now, let's discuss the actual consumption of the output of this technology. This is critical because unless a technology is able to be consumed in an intuitive, visual, easy manner that works its way seamlessly into the operational habits of the end user, then it's pretty much useless. It might be the most exciting thing in the world, but you have to find a way for it to be part of the daily life of the end user. So how can we consume real time? This is a fundamentally different question because typically statistical analysis and analytics would be consumed on a, say, weekly basis maybe, daily at best, using reports effectively. So you would build a report and maybe fold it into a PowerPoint or a Word document. Of course, there are certain areas where a lot more advanced operational processes were in place, like computational finance. But generally speaking, in business intelligence, the report was the key method of consumption of statistical insights. But with real time, we want to disrupt that. We want to have something more agile and more readily available. How can we do that? There's four main ways that I've encountered in my work in both industry and academia in which you can consume insights from a real-time machine learning module. Number one is an always-on method of consumption, where you have a live dashboard that displays at all times what the current situation is in the environment that you're trying to track. We have an example here of a dashboard that we've built for threat detection on computer network traffic and available via the Amazon cloud. I will talk a bit more about this later. That's number one. Number two is just-in-time consumption. So rather than having a dashboard which is always on, you have an ability to pull a dynamic report which is up-to-date to the second at the point of request. So this is a pull model where the user decides that they're interested in a piece of information, the profile of a household in terms of their energy demand at this point in time, and they can, at the click of a button, obtain up-to-date information on that variable. So just-in-time is the second way of consuming real-time insights. Real-time is a different way of consuming, yet again, where the system alerts you when something interesting has happened. So the assumption there is similar to the dashboard setting in that the user is assumed to be always accessible by the intelligence layer, but they're not meant to be staring at a screen all day. Instead, they're doing, they're going about their daily business, but they have an email capability or a pop-up message saying, right now, something interesting has happened, can you please have a look? This is the typical scenario in areas like intrusion detection and threat detection in cybersecurity. So for instance, you could have a system like the one described here, where multiple hosts are tracked for indicators of fraudulent or threatening behavior, and then a decision is made by the system on the most likely attack type, in this case, exfiltration of personal data. The security analyst is then alerted and takes action or not, depending on their personal judgment. So this is a decision support tool, right? Alerts are the most natural way to have real-time decision support. But the dream really is fully automatic decision making. In that case, there's no need to consume the insights. There's no need for a human to consume the insights. The insights are themselves the drivers, quite literally in this picture, of a robot of some sort, an automatic decision-making system that helps replace the human in certain activities that are too high velocity or too high volume to be performed successfully by a human. So we've discussed statistical know-how, and we've discussed the idiosyncrasies of consuming insights in real time. Now let's focus on the infrastructure. Clearly that's very important. How is in-motion data handled differently than big data in terms of infrastructure? Well, the big data success story when it comes to infrastructure was very much revolved around Hadoop and distributed processing. For in-motion data, the objective is instead streaming processing. So what are the available tools today to do this? Well, there are plenty, and this is why 2015, I believe, is going to be the year of streaming data and in-motion analytics. The reason is that in 2014, there was a simultaneous maturity of several technologies in this space that have been around for a while, but they only really gathered critical mass very recently. Starting from the right to the left, we have Storm, which is an open source protocol for streaming processing that has a very vibrant community in the Silicon Valley and the UK. And it basically is able to process real-time data flows in a parallel, very low latency manner. Amazon launched its Kinesis platform, which is an implementation of a similar type of architecture as Storm on the cloud, and it's accessible under a pay-as-you-go model. This is where we're building our first product, datastream.io. And on the enterprise side of things, at the far left, there's the big players, IBM, SAP. They're all entering this space with bespoke products that are specifically designed to handle high-speed, high-velocity data streams and process them on the fly. We have done work, for instance, with InfoSphere Streams, which is the IBM product. And again, you can think of it as a robust, slightly less flexible but more reliable version of Storm. So on an abstract level, the key features of an infrastructural layer that can handle streaming processing for in-motion analytics are the following. You need multi-threading and parallelization because you have multiple data feeds coming in. And the last thing you want is a bottleneck where all the data have to be queued in the same queue in order for them to be processed. Remember that in most natural settings for in-motion data, like the Internet of Things, there's a huge distributed component to the equation, right? Because all the sensors are totally independent from each other and they're generating data independently from each other. So multi-threading and parallelization are very much bread and butter in the business of in-motion analytics. Now, the obvious second requirement is streaming low latency processing. That's obvious. And finally, you need to have the ability to both process regularly and reactively. By this I mean, maybe the best analogy is the push-pull architecture. Typically, you would have a pull architecture when it comes to analytics. The code that generates the report or the analytical insight requests some data and then processes it. In contrast, in streaming environments, the idea is that you need to have a push paradigm as well, where the data come in from the sensor and they trigger an analytical processing element to do its job. So you need to be able to accommodate both a push and a pull paradigm when it comes to processing in-motion data. So that is my short discussion of infrastructure, and now I'm going to talk about domain knowledge. How can we best make use of domain knowledge in in-motion data analytics, and how is that different from what we've been doing up until now? So in the batch paradigm, experts, domain experts, will generally suggest appropriate model structures. For instance, if you're a classical statistician, they might suggest appropriate priors if you're a Bayesian statistician, and they might also label a training corpus for you. For instance, if you want to classify a set of documents as belonging to one of several topics, ranging from, energy, utilities, environment, law. Then you might start with a corpus of such documents labeled by a human expert, and then you use that corpus to train your machine to classify new documents. So this is typically the way in which experts contribute to the learning process. It's by an initial seeding phase, if you like, where the expert guides the analytical engine into the direction that is most useful to them, and then the learning takes place and the consumption of the outputs takes place last. But when we have a real-time system that is deployed in a real-time setting, we need to have a continual feedback loop between the machine and the expert. The expert consumes the machine output and then needs to give some feedback about its relevance and accuracy to the machine. So in this continual learning paradigm, everything is different. Regular feedback, as opposed to a one-off feedback session in the beginning, is crucial. The reason for that is what we discussed before. Everything changes, and consequently your method needs to adapt to these changing requirements. But if part of this change is, if you need, for instance, the labels in the documents in order to detect that change, then the human must be in the loop. They must keep you informed about the accuracy of the method. To put it more simply, if the accuracy of your machine learning method relies on human feedback, then that feedback needs to remain present throughout the learning process, and therefore it needs to be continual. Moreover, expert feedback will depend on the consumption model, right? So we discussed 4 different consumption models. For instance, in the alert, in the case of real-time alerts, you need to have some way for the expert to tell you, actually, this was a false alarm. This is invaluable information for the learning engine. In the fourth use case, where we have fully automated decision-making systems, usually there's no expert involved there. Like I explained, in those cases, the objective is usually to predict something or react to your environment in a way whose success can be measured automatically. So in that last case, you don't actually need user feedback. But in the other three cases of dashboards, alerts, and just-in-time dynamic reports, you need the user to be involved somehow. The distinction between unsupervised learning and supervised learning is therefore critical. Unsupervised learning is a type of learning that doesn't require human feedback. The data have all the information that's needed to perform unsupervised learning. The classical example of that is clustering. If you want to cluster data points into groups of similarly looking items, you don't really need a human to validate that process. You can do it automatically, in contrast to classification, where a label is needed for the machine to learn the relationship between the label and the object. So in unsupervised learning, human feedback is not needed, and consequently my personal view is that unsupervised learning is best suited to streaming data and in-motion analytics, because it doesn't require the user, the expert, to be continuously available to the learning engine for feedback. However, some feedback is always needed to guide the engine. Consequently, semi-supervised learning, where the engine is able to continue without any feedback, but is also able to incorporate any human feedback that it may get its hands on, is probably the best type of technology for in-motion analytics, and definitely the core of our machine learning toolbox in Mental. So, at this point, I'd like to make a short pause for any questions that the audience might have until now, because I'm about to do a deeper dive into the mathematics that underlie some of this statistical know-how. All right, we can move on and take any questions at the end. So, I'm now going to speed through some interesting mathematics that are needed in order to do full-scale machine learning on data streams. I'm going to focus on three aspects. The first is what it means for a method, a model, a pattern recognition tool to be up to speed. I'm going to explain what that means from a technical perspective. The second thing I'm going to focus on is the simple operation of tracking an average. Let's assume that all you want to know is what is the average meter reading for a household in the UK, but you want to track that because it might be changing depending on the season or other unpredictable factors. So that's my second focus point, how to track an average, as simple as that. Finally, I'm going to talk about classification a little bit. How does concept drift, which is the technical term that the classification literature uses for the observation that everything changes, how does concept drift affect our, beloved classifiers such as neural networks and linear determinant analysis and so on. So we're going to talk a bit about that with a specific example coming from credit scoring. So let's start with being up to speed. What does that mean? Right, so I'm going to reiterate here that the batch paradigm of doing analytics involves a data stream. I'm going to call that now x1 to xn. Each xi is a piece of information, and we have n pieces of information so far that arrive continually over time. These are typically stored in a database, and then the analytics engine makes multiple requests back and forth from the database in order to produce some output. This output can be a model if you're a statistician, a pattern if you're a data mining guy, or some sort of prediction if you're a machine learning guy. So I'm going to call that theta hat n. And the reason for the hat is that it's an estimate, right? It relies on the data. It would be different if we had seen a different set of data. And the subscript n is means to indicate that theta hat has seen n different data points. So it has seen the data history from day 1 to day n. Now, the big data setting is fundamentally the same, except that the algorithm needs to be able to access a potentially distributed data storage system. So there's really no difference as far as this talk is concerned between big data and small data. It's, the main difference comes in when we want to work in streams. So in streams, the premise is that storage is an option that you have, but it's not a core key part of the system. The algorithm continually ingests the information and updates its model output, that phi hat n quantity that I talked about. So the objectives in the academic literature have mostly been to be online, which means to have a model update rather than a model refit cycle, and to be adaptive, which reflects the need to track potentially evolving dynamic systems. I'm going to mention at this point that this is a gross oversimplification of what it means to do in-motion machine learning for the reasons that I described a while ago. So all of the other aspects, such as the exact requirements of the infrastructure, the exact mode of consumption of the output, as well as the best ways to introduce human feedback into the loop, these are critical considerations for any system that has a chance of success in the real world. But the academic literature on streaming data has focused only on being online and being adaptive as the two main considerations, and that's the right call for an academic to make, because these are already extremely challenging. So we have to abstract away some of the aspects of the real world in order to make any real progress. So this is a window. A window is the cornerstone of most streaming data systems that are in operation today. What do I mean by a window? The term window is used in this context to indicate a method that only looks at the, say, 3 last months of data. And you roll that window as you go along. So today I'm going to look at the 3 last months of data. In a month's time, I'm going to move my window and I'm only going to look at 3 months starting from that date. So the size of that window depends on the computational powers of your algorithms, as well as your beliefs about how quickly the process is changing. If you're looking at something like earthquake data, you might want to have a window of a few years. If you're looking at financial high-frequency data, you might want to have a window of a few seconds. I'm going to come back to that. But this is simply an illustration of what I mean. If your process is changing and you want to have up-to-date information on what the average value of this particular time series is, for example, then using a window allows you to focus on the most recent data. And in most cases, it's the most recent data that matter the most. So when you want to know what's happening right now or in the next few seconds, historical data tend to have less importance. I'm going to revisit exactly the meaning of that sentence in what follows. Now, the strength of the sliding window, as this is known in the literature, is that it's a one-size-fits-all method. No matter what your model is, no matter what your machine learning tool that you're using is, no matter what your data mining algorithm is, you can always implement it and deploy it in a real-time setting by using a rolling window, sliding window. You simply refit the model, you rerun the pattern recognition tool every day using the last W days of data. Moreover, quite surprisingly, it's fairly hard to beat in terms of performance. It's very stable because it doesn't have complexities. It's very easy to implement. So in practice, it's really extremely popular, and I dare say for good reason. However, clearly, it's unsatisfactory. So let me explain what I mean. In the current academic literature, for those of you that are mathematically and statistically inclined, there's been huge success over the last 10 years in developing models for processing dynamic systems. In particular, the particle filtering literature, which is a very novel way of doing Bayesian analysis on the fly on dynamic settings, has literally exploded. So we have an increasing number of interesting papers in this area every day. Now, classically, the time series literature would be the one to handle temporarily evolving data, but the problem with time series methods is that most, in the dramatic majority of cases, they require multiple visits over the data history. So although they handle changing distributions, evolving data, they need access to a history in order for them to be able to fit their models. So they're not really applicable in the streaming domain. Now, I'm trying to plot here a picture of the ecosystem of available methods that we have for doing analysis of evolving data. And classical time series is very dynamic in that it's able to handle change, but it's also offline because it requires access to the data history, multiple iterations of it. Now, maximum likelihood estimation, which is an optimization method that has very solid statistical principles and gives an estimate theta hat n of the parameters of a specific model given a data set, is neither dynamic, because it assumes that the data are independent and identically distributed. That is a technical term that means that the process that's generating x1 on day 1 of my system is exactly the same as the process that's generating xn on the nth day of my system. So that makes this approach static. It doesn't have a dynamic character, and it's also offline, because it doesn't actually have an inbuilt capability to process information as it arrives. It requires multiple passes over the data. However, recursive MLE is a way to do maximum likelihood estimation in an online fashion. I'm going to discuss this in a second. Particle filters and Kalman filters are approaches that are able to have a dynamic character and still satisfy the online processing constraint. And Windows sits there in the middle as a one-size-fits-all but low accuracy method. So let's now dig even deeper. So the first equation here is the classical batch paradigm. My theta hat t is my current estimate of my model parameters, or my current representation of the rules that my data mining method has discovered. And this is basically, you can think of it mathematically as a function of a data set, x1 to xt. Now, this function requires access to all of the data simultaneously. And that is the problem that we face when using offline tools in streaming domains. We don't have the luxury of utilizing functions, pieces of code that need access to all of the data simultaneously because we haven't stored it. So there's two ways to understand how to replace F here by a counterpart which is better suited to streaming data. One way is what we call a recursive exact solution. A recursive exact solution is a way to obtain theta hat t exactly via an update of its previous value, theta hat t minus 1, and the new information xt. In this case, there's equality. So doing this online is exactly the same as doing it offline. Only very simple statistics and models can be updated in this fashion, such as an average. I'm going to come back to that in a second. Anything more complex needs to rely on an approximate update, where the model update function g is only approximately equal to what you would have got had you had the luxury of looking at all of the data simultaneously. This is the context in which we operate, what we call an online single-pass algorithm. So the term online makes a purely computational statement. It says that my update function has constant computational requirements over time. Its computational requirements do not grow as the data grows, and this is a key, an absolutely necessary condition for anything to work in streaming data. Sometimes you can actually handle logarithmic requirements in time, but I'm not going to get into that technical detail. Now, as for adaptivity and tracking evolving systems, we might want to spend a minute here to visualize what change means. Data streams are often called drifting or evolving to emphasize the possibility that change that hasn't been foreseen can occur, and that change can be of various types. The most common type is smooth drift, whereby the process is changing slowly over time. Here I'm plotting three ways of tracking the average value of the asterisks over time. One is a static solution that's represented by the dotted line, and as you can see, the dotted line, the best it can do is form an average of what it's seen so far. It has no inbuilt ability to recognize that the process seems to be changing over time. Consequently, its value is basically off almost all of the time. And this might be a toy example, but this is certainly my experience working with streaming data in real life, that most offline tools that are currently available in statistical software are going to be dramatically off, precisely because real-time systems change. Now, an adaptive solution, such as a sliding window, will of course be better in tracking the asterisks as they evolve. But if you choose your window size to be too small, so if you're tracking too locally, you might end up with a process which is very variable, very volatile. It gets thrown off in various directions by just random noise in the data. This is a key consideration here. If today's meter reading is very far from yesterday's meter reading, your learning algorithm needs to make a choice. The choice between deciding that this is a genuine change in the process, that something has changed in this household, versus the alternative of that just being random variation that should be ignored and averaged out. This is a constant dilemma in statistical know-how that is applied to streaming data. What I describe this here as an optimal solution is a solution that is able to track the change in the data without getting confused too much by the random variation. Regime change, in contrast, is a different type of change where that occurs abruptly and persists thereafter. So here, at the middle of the time horizon, there's a sharp jump from a value of around 1 to a value of 2, and our method needs to be able to track this, again using a static tool that looks at all the data history as if it's all coming from the same process. Would be accurate at first because in the first part of the time horizon the data is pretty static, but as soon as a change is introduced it becomes irrelevant. It's averaging out two regimes that have nothing to do with each other and consequently learning a value which is not representative of the data at any point in time. That's why adaptivity is so key. Finally, we have the problem of outliers. Outliers are observations that for some reason or other are totally unrepresentative of the data stream and in reality should be ignored or flagged as potential faults and reasons to worry, reasons for concern. In any case, they shouldn't form part of what your model thinks is normal behavior. So this is another very common problem in streaming data because when you have a real-time sensor network deployed in an urban environment, in a dynamic environment, sensors go wrong, they get stepped on, they run out of battery, and consequently all of these issues can cause very short-lived but dramatic disturbances that need to be handled by your system. So robustness is key, is the message that I'm trying to communicate. When you're building a system that is meant to be operational at all times, you don't really care about it being optimal at any given point in time. What you care about is for it not to completely break down eventually. And this is what I call the adaptivity principle. I have a theory that every single continually operating machine intelligence will eventually fail, unless it's been designed with that in mind from the beginning. So local estimation, which is a generalization of sliding windows, effectively it's the premise that you only look at data local to your current time point, is a fail-safe in the sense that it allows for a way out of the adaptivity principle. However, it's not always ideal because it's not able to handle recurring patterns on long memory processes, right? So it has its constraints. I like to think about this as a very huge area of future growth in both statistics and technology. It's the two extremes of learning, forgetting, and everything in between. If you remember everything, eventually your knowledge becomes obsolete. A bit like, my grandfather wondering what an iPhone does. If you're too adaptive and you only look at the last few days of data, then you lose out on valuable information, right? So you're like a child that doesn't have enough prior knowledge to pursue complex tasks. So you need to trade that balance very carefully in streaming data. So I'm going to go very fast over the next few slides because this is a resource that will be available to everybody following at the end of this talk, and therefore I think this information is good to be there, but I don't want to tire you too much with it. This is a very simple example of tracking an average, and in the static case, all I'm going to show you is the first part of the leftmost part of the first equation, where the average, which is the output of our model in this case, is just literally the average of the t-values that we've observed. Now, we may express this in a recursive form as what we call in mathematics a convex update. So it's a linear update between the previous value that we had for the average and the new information. And this quantity eta t, which controls how important the new information is versus the historical, the old, if you like, value of the average that we had, would in this case be exactly equal to 1 over t. So it would vanish over time. And that represents what we call in statistics convergence. If you believe that all of the data are coming from exactly the same process, then your views about the world, about this process, in this particular instance, the very simple notion of an average, should eventually converge. It should stop reacting. It should stop responding to new information because it's learned all it can about this process. So the key message from this slide is that if you assume that the data are coming all from the same process, if you assume a static setting, novel information will matter less and less. Now, there are several ways to modify this to introduce adaptivity, to break down that assumption. The rolling window is one way, and here's the maths for it. It's very simple. You simply look at the last W observations, and you take their average. Now, it's possible to implement that solution recursively so that you don't actually need to store the observations themselves. But given that you're only looking at W observations, that's possible to store online without your memory requirements exploding over time. So this is by construction online, and it is by construction temporally adapted. However, it's very unnatural. You don't really believe that the observation at t minus W was entirely irrelevant, and that the observation at t minus W plus 1 is as relevant as today's observation. And that is precisely the assumption that the window is making. And this assumption is unrealistic. Before that, whereas exponential forgetting, which is the idea of smoothly down-weighting past observations, offers exactly that, a smooth decay, which is a more natural assumption. Now, there is a mathematical relationship between windows and forgetting factors. You can exactly identify how many data points a specific value of the forgetting factor stands for. And it's been a very popular approach beyond machine learning. It has a long history in adaptive filtering in signal processing. I have great respect for signal processing engineers. They've been working with these problems for longer than we have in statistics and machine learning. And it's also used in some time series methods. So I'm going to skip that slide, except to mention that there is a very neat mathematical way to express sliding windows, forgetting factors, as well as static estimators in exactly the same form, that of a convex update. The key quantity that differentiates these methods being eta t, which we call a learning rate. That is a parameter that controls how important novel information is in comparison to historical information. Stochastic gradient descent is a way to generalize this approach in methods that have more complex statistics that are being tracked than a simple average. And stochastic gradient descent underlies a lot of recent success stories in machine learning, such as deep learning, and it is very much the core of our machine learning toolbox at Mentat. The idea is that you have a loss function that measures how well you're doing, some sort of accuracy metric, and at each new time step, you try to optimize that function by moving a little bit in the direction of the gradient of your accuracy function with respect to your model parameters, your model representation, evaluated at that last observation. So you don't actually look at the gradient of the entire loss function, only at the most recent contribution to that loss function from the new data point. Now, the take-home message here is that in all cases, gradient descent, forgetting factors, sliding windows, there is one parameter which is critical in that it determines how much novel information matters. And there are ways to make all of these approaches be slightly similar to each other, approximately equivalent, by setting these parameters to the same value, which goes to emphasize the fact that in streaming learning, really you have to have a prior belief about how quickly things change. And this is a very difficult prior belief to have. It's much easier to have some belief about the structure of a model or the potential relationship between variables than to have a prior belief about how things change. This is a very difficult question to formalize. So this is a key problem faced by all machine learning in motion settings, and it's very much the core of the technology that we're developing at Mentat, as well as my research at Imperial College London. Now, I'm going to skip through the rest of the technical slides because I want to leave time for questions. Like I said, my slides are a much richer resource than the time that I have for this tutorial would allow for, and please feel free to peruse them at your own time and ask me any questions that you have. So let me just scroll through these slides. So I'm going to stop at this slide here and discuss the future of this area, if you like. So far, I've been representing my model by a quantity theta hat t. This is what we call a parameter in statistics. For computer scientists, you can think of it as a finite dimensional state, right? So it's a state whose size doesn't grow with the data. However, we need to be able to go beyond parametric estimation because very, modern statistical tools and modern machine learning tools are often not simple enough to express in this parametric estimation framework. Examples of that include histograms like the one on the bottom left of the screen, Markov processes that might describe a process that ranges from trying to log in through to an exfiltration attempt in a security context, or word clouds, which are a way to capture linguistic information in a text analytics context. So all of these methods are not simple enough to fit this framework of stochastic gradient descent, which I illustrated very rapidly before. They're far more complex, and therefore the question of how do you update a word cloud, how do you update a Markov model, how do you update a histogram, these are very much open questions if you really want to do it in a principled fashion. And we at Mentat try to be at the very cutting edge of that literature and make sure that all of our machine learning toolboxes squeeze as much information as they can from the novel data point, from the new information, and they use that information to inform their method, but also to understand whether things have changed, these two requirements that I've been talking about. So to sum up, everything changes in motion analytics, and this changes everything. Data streams are arriving in real time at fast pace. Your statistical know-how is transformed by this because you need to have methods that scale with data velocity, and therefore they need to be updated very quickly. This poses methodological challenges that are not at the moment fully resolved in the literature. The infrastructural question is difficult. We're only now starting to have mature technologies in this space that can handle high speed, high volume, multiple data feeds, and process them in both a push and a pull framework. And incorporating domain knowledge into this loop, into this learning loop, is a huge challenge that hasn't really been addressed. The technology hasn't been widely adopted yet for user interaction systems that incorporate human feedback whenever that is available. And finally, the consumption of the output of these methods is still an open question to some extent. There are very fascinating user interface and visualization opportunities in that space. And a lot of industrial sectors still need to be educated, if you like, about the potential. But this is very much the future. There's no doubt in my mind, and in the minds of everybody that I've talked to in the space of big data and machine learning, that real-time is the direction that we're headed at. The true potential to let computational intelligence drive decisions, bring efficiencies, generate new value from data, lies squarely in the streaming data domain. And the reason why this hasn't been done yet properly and why it's such a big opportunity is, as I've hoped to have shown you, that it's technically quite challenging to do anything more complex than simply counting on data in motion. The risks are greater because you don't have the benefit of hindsight. You don't have a way to refit your model if you look at your report and you think it's not that good. You can choose a different model. That's something that statisticians do all the time, and data mining sections in big enterprise does all the time as well. You don't have that luxury when the system is operational in real time and needs to offer insights that will drive instant reactions from the organizations, or even drive automatic decisions, like in the case of a self-driving car. So all of your system needs to be very robust. And this is the vision that we have in Mentat. Mentat has a team of 2 founders, one of which had a background in finance and data intensive analytics for over 20 years. I've already mentioned my own credentials and we have an advisory board of world leaders in the space of data mining and machine learning. And our attempt is to build an intelligent real-time learning layer, if you like, that allows machine intelligence to seamlessly complement human decision-making. And I'm emphasizing the word seamlessly here, because the problem is how to be able to operationalize this knowledge. This is the key challenge now. And operationalization of machine learning requires two things. It requires consumability of the output, which we've already talked about, and also robustness. The method needs not to break down eventually. And this is what the case is with most off-the-shelf methods, because they were designed with static batch contexts in mind. So I'm going to finish with a statement by one of my favorite science fiction books, The Dune by Frank Herbert. A mentat is a fictional job in that book, which is a human required to handle huge amounts of data. And their first premise is that a process cannot be understood by stopping it. Understanding must move with the flow of the process. It must join it and flow with it. And this is exactly right. This is what I call the adaptivity principle. And I think that exact insight applies to machine intelligence in real-time settings. I want to thank EY for hosting this webinar at Level 39 in Canary Wharf in the context of the EY Startup Challenge competition. And I also want to mention that we're about to join Cisco as a winner of their Entrepreneurs in Residence program in Vienna, where we're going to be looking at Internet of Things and smart cities in collaboration with this huge IT company, and we're very, very happy to enter that phase. So thank you very much for listening, and I'm free for any questions that you may have. What about unstructured data? So I've already mentioned word clouds at some point in this presentation, and unstructured data in itself is not a problem because you can still handle it in a streaming fashion. It's the models that you use that you need to think about. So most models in unstructured data have themselves a structured representation. So let me explain what I mean. The data is unstructured. It might be a JSON object involving pure text, but the model itself is stored in a structured format that involves certain parameters, decision rules, word frequencies, cluster allocations, and so on. So the attempt that you need to make there is to understand how to update the model parameters in a streaming fashion. So images, video, all of this is in effect boiled down by the machine learning algorithm to some parameter, some representation of the insight that you're trying to extract, the information in the data, if you like. And it is this information that you need to worry about and attempt to update in real time. I hope that answers the question. The second question is, some streaming analytics products have an SQL API to their server. Do you see SQL as a useful API to analyzing data in motion? Well, it's certainly useful to explore data in motion. But in order to have full-scale machine learning on it, usually you need to predefine the SQL query that you want to be tracking in real time. So if you want to build a model that captures relationships between a set of variables, then you need to decide that in advance and build an SQL query, which is then monitored in real time. Now, if you decide to change your model midway, you'd have to adapt the SQL query. So yes, in a sense, an SQL API is a great way to take care of this first step. Let me just scroll back. I seem to have lost control of the screen. Sorry about that. So there we are. So it's a great first step to interface the data stream with the intelligence layer, but it's not going to help in itself to do the machine learning. SQL is about exploring data, potentially counting stuff also, but not doing full-scale machine learning. So if there aren't any further questions, I'd like to thank you all for listening. I will make the slides available, and please visit www.ment.at for looking at our current work and getting in touch with me about any further questions. You can also find me at my website at Imperial College. Thank you very much for listening, and we're very excited to be able to share our vision about computational intelligence that permeates our living environments in the years to come. Thanks again.
Thank you very much, Christoforos. Excellent webinar. Just a reminder that if you'd like to come and meet Christoforos on the 29th of January, he's going to be presenting at the Real-Time Analytics Conference in London. Details of that can be found at unicom.co.uk. Thank you very much. Goodbye.
Goodbye.